Good morning, students. So this class we are going to see about a single external ROM for both code and data. Okay. So here a single external ROM chip is used for both program code and data storage. Here we have considered 8031 based system which is connected to single 64K x 8 external ROM chip. So in this case, a single chip can be utilized for both storing your programs as well as your data. So that case, the entire program space is divided into two. One is specifically allotted for storing your program code and other one is for data. Okay. So here 000FFFF4X are divided into two memory space. That is 00027 F is allocated for storing your program codes and address space 8024F is allocated for storing your data. Okay. So for this particular case, we have to use MOVX instruction for accessing both your data as well as your program codes or instruction codes. Okay. So this is the overall structure for interfacing single external ROM with 8031 microcontroller. So to access both program code space and also data space, we have to use AND gate for this particular interfacing diagram for combining your read bar signal along with your program store enable. So read bar is used to access external data space. This is for accessing external data space. And program store enable is for accessing external code space. So both the spaces that is both your program as well as data are stored in this ROM memory. In order to differentiate your program space and data space, we have to incorporate this AND logic to separate your data space and program space. So here read is used to access your data space and program store enable is used to access your code space, and remaining features, the remaining connections are very similar to your previous interfacing diagram. That is P2 is connected to A15 to A8 of A8 address pins of your program or data ROM, and also your P0 is connected to the address pins A0 to A7 of your program or data ROM, and your chip select enable is grounded. Remaining connections will be same. EA is grounded because everything is stored externally. So EA must be grounded here. The only difference to separate your data and program space here, AND gate logic is used to access your code space and data space. Okay, is that clear? So this problem is very important problem. So it may be asked in your final exam for 11 marks. Okay, listen carefully. So this structure, that is 8031 memory interfacing, that is connection to external program ROM. Here we have program ROM, data RAM and data ROM. Okay. So please look at the connections. So here EA is grounded. Okay. And read bar. What is the purpose of read bar? To access the external data space. Okay. So this read bar is connected to your data ROM. Okay. Similarly, your program store enable is connected to output enable pin of program ROM. So read bar, program store enable, these two signals are used to differentiate your data space and program space. And coming into the data ROM, the chip select is generated by using this 74LS138 decoder. I have explained already. So here two select lines are used, that is A14 and A15. C is grounded, everything is grounded. C, G2B, G2A, all are grounded. And here we have four outputs, Y0 to Y3. So Y0 is connected to the output enable of your data ROM, and Y2 is connected to the 16K cross 8 data RAM. Okay. So in order to generate your output signal, suppose your AB00 means your Y0 is generated. 01, Y1 is generated. 10, Y2 is generated. 11, Y3 is generated. Okay. So 00, Y0 will be generated. 01, Y1. 10, Y2. 11, Y3. So in that case, here your program ROM, so chip select can be generated by using the 74LS138 decoder for your data RAM and data ROM. For program ROM, only the address lines from A13 to A0 is utilized, and A14 and A15 are ignored. So you can put 00. So only A0 to A13 address lines are utilized for program ROM. Remaining two address lines are unutilized. Okay, because A14 and A15 involved in your Y0, that is your Y0 and Y0 to Y3 output generation. So this A14 and A15 are ignored in the case of program ROM. So here what we have to do is, first we have to identify the address space for these three IC first. The question is, find the address space of data RAM, data ROM, and program ROM. Please find out. So first, we will start with the data RAM. So data RAM output line, that is your chip select enable, is connected to Y2. So what is the combination for Y2? Please tell me. What is the combination? 1 0. So your A15 1 and A14 0, remaining all address lines will be 0. So what is the address, starting address? Starting address of the address range? So what is the address? 80. Okay. So next case, to calculate your end address, 1 0, remaining all the address bits are 1. So what is the answer? B triple F. Okay. So please note it down. For 16K cross 8 data RAM, the address range will be 8000 to B triple F. Okay. So next one, 16K cross 8 data ROM. So your chip select that is the chip enabled is activated by using output line Y0. Okay, so 0 0, your A14 0, A15 0, all the address lines will be 0. So the starting address will be 0 0 0. Okay, and what about the end address? Students, are you able to follow? Okay, 0 0 0 to 3 triple F. So that is for your 16K cross 8 data ROM. Okay. So what about 16K cross 8 program ROM? So that case A14 and A15 are ignored, and A13 and A0 will be 0 for your starting address, and for calculating end address, A13 to A0 will be 1. So what is the address? So what is the address? So here, one second. So your first case, Y2. So 1, 0. So this is your A15 and this is your A14 and all the bits are 0. So the answer is 8, 0, 0, 0. This will be your A0. Next case, same 1, 0, A15, A14. Remaining all the address bits are 1. So B triple F. Is that right? B triple F. Okay. So next case, why not? For next IC, that is 16K cross 8 data ROM. That case, 0, 0. A15 and A14 will be 0, 0. And all the bits are 0. The starting address is 0, 0, 0. Okay. And next case, 0, 0, 1, 1. And all the bits are 1, 1. So 3 triple F. So next one, 16K cross 8 program ROM, A15 and A14 are not utilized. That is 0, 0. It's always 0 for both your starting address and end address. Okay. So remaining 0, 0, 0, 0, 0, 0, all 4 zeros. So the address is 0, 0, 0. Next case 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So 3 triple F. So the first, this one, 300 to 3 triple F are allocated for data RAM. So same address. So this is for data ROM and this is for program ROM. So same address will be utilized by two different IC. One IC is for data, storing data, and another IC is for storing your program. For storing your data, we have to use MOVX instruction, and accessing your program codes from program memory, we have to use MOVC instruction. So that is the difference. So please go through the solution. So the first case, A15 and A14 have to be 1, 0 in order to select our chip. So the address is 8,000 to B triple F. And next case of data ROM, A15 and A14 have to be 0, 0. So the address range 000 to 3 triple F. So in the case of program ROM, the address line A14 and A15 are not at all used because since it is involved in address decoding, so A15 and A14s are don't cast. So you make that A15 and A14 set to 0 and address space 00 to triple F. So both the address will be same even though it does not create a clash with the address space of ROM and RAM because different instructions are used to access your code space and data space. Is that clear? Is that clear, ma? Yes or no? Is that clear? Students, please reply. Gala Meenakshi, Venkat Ramani, are you able to follow, ma? Any other doubts? Okay. So this is the first question. So find the address space of data RAM, data ROM, and program. So next, write a program to access a byte of data which is in data ROM. So data ROM. So divide that value. You have to fetch the data from 16K cross 8 data ROM and divide that value by 2. Okay. And save the quotient in the data RAM. So that is the different memory. So you get the data from data ROM and divide that value by 2 and save the quotient in data RAM. Okay. So for that, So please look at the code given here. It's a very simple one. You have to carefully use the address based on this calculation. Okay. So first, what is the first memory? According to your problem statement, you have to access a byte of data which is in data ROM. So the data ROM starting address 0002 3 So the starting address of memory 00. So initialize your DPTR to 0.000. So get the data from your data ROM. Okay, so this is the starting address of your ROM and access the data from 000 to accumulator and divide that value by 2. Okay, according to the problem statement, we have to divide the number by 2 and save the quotient in data RAM. So what is the address of data RAM? 8000. So initialize DPTR with 8000, move that value into our DPTR. So in this way, we can transfer the data from one memory IC to another memory IC based on address decoding. Is that clear? So your first location in data ROM 000. So your DPTR is pointing 000. Get the data and move the data into accumulator using move X instruction and divide that value by 2 and store your quotient in the data RAM. Okay, so starting address of data RAM hash 8000. So you make DPTR to 0.8000, move that value to 8000. Is that clear? It's a very simple logic, but you carefully note down your address range. Based on the address range, you have to transfer your data from one IC to the another IC. Okay. So next statement is, so rewrite the same program for the case that data byte is in program ROM instead of data ROM. Okay. You have to access the data from program ROM and divide that number by 2 and save the quotient in the data RAM. So that is the problem statement. So to access data bytes in program ROM, we have to use move C instruction instead of move X. So that is the difference. So whatever element you are accessing from program ROM, for that case, we have to use move C instruction. So here, so assume that the required data has already been burnt into the location 0100 H of program ROM. Okay, so already it has been stored at memory location 0100. So that will be the address. So move that address into DPTR. Okay, here we have to use move C instruction. So the format for move C syntax is A, A plus at DPTR. So initially clear accumulator. Okay. So clear your accumulator. So 0 plus 010, the address will be 010. Here we have 8-bit data. So transfer that data to accumulator. Okay. After that, divide that value by 2. Okay. After the division, you have to move the data into data RAM. Okay, so data RAM starting address 8000. So initialize DPTR with 8000, move that value using a move X instruction, move that value to DPTR. So in order to access data bytes from program memory, you have to use move C. If in the case of data space, you have to use that move X instruction. Any clarification regarding this? So it is a very important problem in this unit. Any doubts? Okay. So quickly, I will explain this MAX232 and your sensor interfacing. Okay. So this is the MAX232 IC. So the purpose is actually RS232 standard is not compatible with TTL logic. Okay. So therefore it requires line drivers such as MAX232 chip to convert RS232 voltage levels to TTL voltage level. So we require some line drivers. So the line driver is MAX232 or MAX233. Okay. So it is designed by Maxim Integrated Products. So this IC is widely used in RS-232 communication system. Okay, the main purpose is to convert TTL level to RS-232 level and RS-232 level to TTL level. Okay, basically TTL level means we have only two levels, 0 volt and VCC. So 0 means logic low, VCC means 5 voltage or 3.3 voltage. So this is about our TTL. Our 8051 supports this TTL logic. Okay. Suppose in case of RS-232, one, that is logic 1 is represented -3 to approximately -25 voltage. Similarly, logic 0 plus 3 to plus 25 voltage. So here the value is between -3 to plus 3. So this one is undefined one. Okay. And also it's very difficult to write programs, that is for accessing your serial port. So most of the IC supports this TTL logic levels. Basically in 8051 we have two pins, TXT and RXT, specifically for transferring and receiving data serially. So these pins are TTL compatible, and also for external device communication or RS-232 level communication, or suppose your 8051 is interfaced with PC, that case we require line drivers for converting TTL level to RS-232 level for transmission. Similarly, RS-232 to TTL for reception. Okay. So this RS-232 comes in 16 pin DIP, dual inline package, and contain dual drivers. So it has dual drivers. An advantage of this particular IC is it uses a plus 5 voltage power supply, which is same as this source voltage for your 8051, which means that the single plus 5 voltage power supply, we can power up both the 8051 and MAX232. It is an important feature of this IC. So there is no need of dual power supply. So there is no need of a separate power supply for 8051 and 232. Single power supply is sufficient. Okay, this 5 voltage is sufficient for both your microcontroller and MAX232. So here you can look at this diagram. Here we have 8051 and this is your MAX232 IC and this is your RS232 connector, EB connector. So 11th pin is the TXT and 12th pin is the RXT. Okay. So sorry, this is 10th pin, 11th and 10th. And this 11th pin is connected to the 11th pin of MAX232 IC. This is the interfacing connection. Similarly, 10th pin of your microcontroller is connected to the 12th pin of your MAX232 reception. So TXT, RXT are connected. At the that is RS232 level output, here 14 and 13. Okay, so 14 is T in out, 13 is R in reception. Okay, so I will explain this diagram first. You can clearly understand the concepts of your MAX232. Okay, so basically it has two sets of line drivers. So this is line driver 1 and this is line driver 2. Okay, and the line drivers used for TXT are called T1 and T2. Please look at here, T1 and T2. And RXT, R1 and R2. So here T1 and R1, T in and R1 are used together for TXT and RXT of 8051. So the second set, that is T2 and R2 set, is left unused. Okay. So here this T1 is the TTL side. This side is the TTL side and this side will be your RS232 side. Okay. So T in is the TTL side and it is connected to the TXT of your microcontroller. Similarly, this T out, so this pin, that is the RS232 side, it is connected to the RXT side of your RS232 DB connector. So this is the connection detail. So here RXT is, TXT is connected. Here this side, this will be connected to the RXT pin of RS232. Okay. So that's all about connection. And here we have DC to DC converter. So this MAX232 IC has onboard DC to DC converter, that is voltage doubler and voltage inverter. So it will provide plus 10 volt to minus 10 voltage and also plus 5 voltage to plus 10 voltage, doubling the voltage. So this DC to DC converter generate the voltage plus or minus 10 from plus 5 voltage, and capacitors are part of on-chip DC to DC converter. So two capacitance C1 and C2. So these capacitance are part of on-chip DC to DC converter. So that's all about your MAX232. It's a very simple concept, that is converting your TTL level to RS232 level. So your TXT pin is connected to the T in of MAX232. Similarly, the T out will be connected to the RS232 level TXT pin. Similarly, reception. So this will be your RS232 level and this will be the TTL. Okay. So the capacitance, 4 capacitance are involved, ranging from 1 microfarad to 22 microfarad. So this is a capacitance selection for different ICs. Okay. So another version, MAX233 and MAX233. So the benefit of this IC, it saves board space. Okay, because it has integrated charge pump capacity. Charge pump capacity. And eliminates the need for bipolar plus or minus 10 voltage here. So only 1 voltage, 5 voltage. So it enables single power supply operation from plus 5 voltage power supply, and all the capacitors are integrated inside IC. Okay. So it performs the same job as MAX232 but eliminates the need for capacitance. It uses no external component and it is recommended for applications where PCB space is critical. So remaining functions will be same as MAX232. So mainly for serial communication. So that's all about your MAX232. Next one, coming into the sensor interfacing. So next topic will be how to interface your thermistor, that is temperature sensor, with the 8051 microcontroller. Basically, transducers convert physical data such as temperature, light intensity, flow, and speed to electrical signals. Okay. So depending upon the transducers, the output produced is in the form of voltage, current, resistance, and capacitance. For example, thermistor. So thermistor means the temperature is converted into electrical signal using transducers called thermistor. So this thermistor responds to temperature change by changing resistance. Okay. So that is the main feature of your thermistor. Responds to temperature change by changing resistance, but the response is not linear in this case of thermistor. Okay. So when the response is not linear means, suppose if the temperature is 0, that is temperature is 0, the resistance change 29.4 kilo ohms. 25, 10, decreasing, 50, 3.8. There is no linear scale here. 75, 1.7, 100, 0.817. So, and while programming this, programming the nonlinear devices is a very tedious process. For that case, the linear temperature sensors are available in the market. So that sensors are LM34 and LM35 sensors. So these sensors are linear sensors. So linear sensor means it outputs 10 millivolt for each degree of temperature change. So based on that, we can convert that value into digital values. Okay. So in case of LM34 and 35, requires no external calibration because it is internally calibrated. So LM34 means It outputs 10 millivolt for each degree of Fahrenheit. LM35 means it output 10 millivolt. That is, your output voltage is linearly proportional to your Celsius. So that is the difference. So these sensors are very accurate sensor. There's a precision integrated circuit. This will respond to the temperature change in linear. Okay. So here there are many versions, variations in LM34, 34A, 34, 34CA, 34C and 34D. Output will be 10 millivolt for each degree of Fahrenheit. And similarly, 35 we have different versions. Your output will be 10 millivolt for each degree of Celsius. Okay. So next we will see about signal conditioning and interfacing the LM35 to 8051. So why the signal conditioning is required means, actually signal conditioning is widely used in the world of data acquisition. That is conversion of signals from voltage, that is voltage, current, charge, capacitance and resistance produced by transducers to voltage. So that is the meaning. That is a conversion of physical signals into voltage and which will be sent to the input of analog to digital converter. So this is the block diagram. Here you can see the temperature sensor. So the output will be in the form of either voltage, current, charge, capacitance and resistance. So here we need to convert this signal into voltage in order to send that voltage to ADC. Since ADC accepts only voltage signal, for that case we are in need of signal conditioning unit. Okay. So this conversion, that is converting your physical signal into voltage, that is called signal conditioning. Signal conditioning can be current to voltage converter or signal amplification. So here, according to your thermistor, the change of resistance must be translated into voltages. So that can be done by using signal conditioning. So this component is very important in case of interfacing your sensor. So signal conditioning can be a current to voltage conversion or signal amplification. So here your author has discussed about this ADC 0848 analog to digital converter. So this IC is interfaced with your 8051 and this ADC has 8-bit resolution with a maximum of 256 steps. So 8-bit ADC. And LM35 and LM34 sensor is interfaced with channel 2 of your ADC, which produces 10 millivolt for every degree of temperature change. Okay. And here we can condition the V-in of ADC to produce V-out of 2.56 voltage for full scale output. Okay. So the maximum sizes, that is step size is 2 power 8. So that is equal to 256. So 256 into your output voltage is 10 millivolt output. So 2560 millivolt, that is equal to 2.56 voltage. So that will be your reference voltage. In order to produce full scale V out of 2.56 voltage for ADC, we need to set V references 2.56. Okay. So here a Zener diode is connected across this part to maintain 2.56 voltage and also it overcome any fluctuations in the power supply. Okay. So your temperature sensor is connected to channel 2 and chip select is enabled by a P2.5 and startup conversion of your ADC is connected to P2.6. So this is the startup conversion signal and 8 data lines. And chip select can be generated by using P 2.4, and INTR is nothing but your end of conversion. So the operations are very similar to your ADC 0808. The only difference is instead of end of conversion, they have used INTR. Okay. So here, so ADC has 8-bit resolution with maximum 256, and LM35 produces 10 millivolt every degree of temperature change. So 256 into 10 millivolt, the reference voltage is 2.56. So suppose if the temperature is 0, your input voltage to the ADC is 0. 1 means multiplied by 10, 10. Similarly, 2 up to 30, 300. And this Vn is converted to V out by using signal conditioning unit. Okay. So here, for example, take this value 300. So 300 millivolt divided by your reference voltage 2560 millivolt into step size 256. 300, the calculation is 300 millivolt divided by 2560 millivolt into 256. The answer will be 30 decimal. Hexadecimal 1E. Please note down the formula. This formula is very important for converting your temperature value, that is the voltage signals, into hexadecimal value. So 1E. In this way, the values are converted into hex. So your voltage divided by your reference voltage multiplied by 256. So can anyone explain the operation of this ADC? So what is the first step? First step of the operation? Can anyone explain what is the first step? So your temperature sensor is actually in our ADC circuit in laboratory experiment. Instead of LM34 or 35, we have connected a potentiometer. That's all. Remaining circuit connections will be same. So what is the first step, students? So which channel is selected here? So which channel is selected here? Channel 2. Okay. So first you have to select the channel based on your select lines. Once the channel is selected, okay, you can provide your 8051 has to generate your start of conversion signal. Once the start of conversion signal is initiated, wait for end of conversion. Once the end of conversion is high, okay, we have to enable this output enable and read the digital value to the appropriate destination. So that is the operation. So here I have entered, that is I have given the embedded C code. So it's very similar to your lab program. Please go through the initialization part. So 2.5 is your read and 2.6 is write, 2.7 INTR, and data bus your P0. I have declared two functions. One is the delay function, another one is converting your values into hexadecimal. Okay. So first you have to configure this P1 port as an input by writing FF to my data and make this INTR. INTR also end of conversion also input pin. So configure INTR as an input pin and disable read and write operation. Disable, deactivate read and write. Okay. So next one, initiate start of conversion and monitor end of conversion. Okay. So when end of conversion is high, activate your output enable. So read bar is equal to 0 and move that data to value. It's a variable and convert that value and display using this function. So the function is, you have already gone through the calculations. For example, ff by 0a means 19. I'm separating the values. D1 is equal to ff by modulus of a, 5. So D1 is 5. Next, D2, I'm taking this value 19 modulus A 5. D3, 19 divided by 0A 5, 2. So this is the calculation. So after calculating the value, you have to move this D1 to P0, generate delay. Next D2, generate delay. D3 to P0, generate. So this code is very similar to your assembly. Only the difference, so based on this interfacing diagram, you have to assign your variables. So here P2.5, 2.6, 2.4 and 2.7 are utilized. Okay. Any other doubts?